Hello everyone, this is a demonstration for the full working of the back-to-back converter, which is developed in the CIES lab here in the University of Western Ontario. So just to give a brief introduction about how do we control a fully working back-to-back converter is, is the way that we have developed over here through Simulink in order to control the Texas Instruments microcontroller F28335. And just to give a brief overview, so over here what you see is the analog to digital converters, which takes in analog signals from the 5 channels which are listed over here. These are actually the DC link voltage, the voltage and the current from phase A, and the voltage and the current from phase B. Then using these various inputs from the system, what we do is that we make use of our modified vector control strategy, which is located in this block. For more information about how to use the modified vector control is to read our 2 papers which have been published. So over here is a method to actually convert an incoming voltage, which is actually a real signal, into its imaginary signal components. Over here we are taking the current and the voltage signals, and it converts into its imaginary components for that particular phase. Then what we make use is a phase lock loop. This phase lock loop takes a signal from one of the switches which I'm making use of over here, and then gives us the sine and the cosines which are going to be used for our DQ control. The output of this block is a frequency, VD and VQ. Then in this block we are converting the imaginary and the real signals for the current into its DQ components using an alpha beta to DQ decomposition method. So this is for one phase, which is phase B. This is actually the DC side, the conversion of AC to the DC side of the back-to-back converter. On this side is the other side of the back-to-back converter, which is converting the DC to the AC of the incoming signal. Next are our controls. So for the controls, this is for the DC link voltage control of the back-to-back converter. This is basically remains the same, which is from our previous video. The next thing is the DC to the AC side control, and this actually is the outer voltage loop control for the system, and there is an inner control loop for the DQ components of the current. So this basically is conventional control that we have for an inverter. What next we do is that we make use of the MD and the MQ components which are coming out of our controls, and then convert it into from DQ to alpha beta, and then use those values in order to generate the PWM signals for our gates. Same goes over here for the other phase. And for our serial port, what we are making use of is some of the basic signals, incoming signals that we need in order to visualize those signals, and that can be used for our papers over here. So this is a basic overall MATLAB Simulink program for that will be making use of for our fully functioning back-to-back converter. So this is a demo for the fully functioning back-to-back converter. Right now our MATLAB program is running, trying to download the program that I just showed a video for, and it's gonna be once it's downloaded, then we're gonna turn on. Now the isolation transformer has been turned on, and as you can see, these are the PWM signals that you see over here. This is the DC link voltage. So right now we are giving a 30 volt input, and we are trying to maintain an AC voltage of around 11 volts. So that's what we are trying to see, that whether we can maintain our output voltage at 11 volts or not. So as you can see over here, the sine wave at the output of our uh, inverter, and we are trying to maintain around 11 volts. So as you can see, the voltage is maintaining around 11 volts. The sine wave, as you can see, is of 60 hertz. We're trying to maintain it. Let us try to run this for another few seconds. So I suppose everything is stable by now, and we are maintaining a good sine wave at the output. So this is the end of the demonstration for our fully functioning back-to-back converter.